Okay, y'all feeling energetic after the coffee? Yeah? Okay. So we have pizza for you coming on the way. Don't think about pizza while you're attending the session. We're going to talk about, Naren is going to talk about how he built a programming language using Go with it. So, have fun.
Okay. Okay, actually, who attended this talk before in DDG Chennai? Good. I can't compare because I didn't prepare much. I just came from a travel yesterday. Okay. So who am I? I'm Naren and I'm independent solution architect. A bit louder. Okay.
Sorry, we don't have mic.
I think I didn't have my coffee. Okay. I'm Naren. I'm an independent solution architect. So I just started going solo 2 months back, and then currently I'm helping 2 clients to build some stuff. So one of the clients is building payment wallet system. I'm helping them to build infrastructure in Go, and the other client is an enterprise client, Mitsubishi, and I'm helping them to build some investment portal. And I'm a privacy enthusiast that after getting tired of giving my data left, right, and center to Google and everyone, I was like, okay, no, I need to do something about this. I feel like people are like peeking into my room every time, even though I'm not doing something illegal. So I thought like I just started replacing Google and G Suite with the products, then to be my account. And that's the core, of course. So if you want to talk about that, and I'm an amateur systems programmer. So I I was kind of unemployed for 6 months. So I had too much time in hand, and I was exploring programming languages and how they were designed. And this talk is a result of that, and that's why I'm a systems programmer. And that's my Twitter handle. You can, I tweet some things that aren't completely terrible. You can hit me up if you have questions or feedback. And if you have anything to talk about consulting, you can just go to my portfolio and find out the email ID. So let's jump right in. So how to write an interpreter? So first you just draw the state diagrams, and then you just write the rest of the interpreter. Right? Okay. Thanks for coming to my talk. Okay, yeah, that's not it, right? So, but interpreters are complicated, right? Interpreters / compilers are complicated. It looks complicated, but if you see some theory or some blog post, and then you open a fully mature interpreter like Python's interpreter or Ruby's interpreter, and you try to read the source code, so you feel like, okay, that is the blog post, and this is the interpreter I have, the code I have, what's happening in the middle. So that's what this talk is going to be about. So we are going to see perfect. Just give me yeah. So what we're going to do is so interpreter is this. Behind the interpreter, there are some intelligently returned recursive logics and switch statements, and of course for loops. So we are going to see that. So the perfect circle thingy right there is the switch statements and the recursions. That's what we're going to see. So this is going to be you won't be learning Go, but you will learn a bit about interpreters and how they are written, and if you what happens if you execute a line of code in an interpreter. And I'll be showing you a lot of pseudocode. It's similar to Go, but it's not Go. And so, okay, you type this into your interpreter or compiler. Okay, I'm going to switch the word or replace interpreter with compilers because it's hard to pronounce. So because and also the line is very thin. If you go on Google interpreter or compiler, you can find out that almost both are same. So what happens if you just put it into your compiler and just execute it? What is the result of A, or what gets stored in A? Huh? Awesome. So yeah, that was fast, right? But even compilers are faster than you. But still, it's not as smart as you. So it needs to go through a lot of things. It needs to read every single word in this to find out that value of A is 11. So these are the basic components of an interpreter. So first one is the lexer and parser, and parser uses a data structure called abstract syntax tree, and then it evaluates after parsing. And the evaluator uses some kind of object system to make sense of the string which you enter. Let's see that one by one. So what Lexer does is it takes in the source code and spits out tokens. The source code is which it just types that A equal to what was that?
5 plus 2 into 3.
Yes, 5 plus 23. So there is just a string. It doesn't mean anything. It means something to you, but not to your computer. So it needs to parse that, or it needs to tokenize that and give some meaning to that. So what it does is, if you're just declaring, oh, it's right there. Okay, so if you're just declaring a variable A like this, it just tokenizes it and it assigns some meaningful tokens to that, and the tokens will have some kind of type associated with it, and so it knows what it is, right? So now it's kind of closer to the machine code, or closer to the representation where a machine can understand. So in order to build the Lexer, you just need to know the different parts of this string. So this latest keyword, of course, you will know this. You would have come across this in any programming language. That is a keyword, and A is an identifier, and these are all literals, and this is just these are all the operators. These are assignment operators and some multiplication or product operators. So with this in mind, let's try to define our token struct. So if you have this, let A equal to 5 plus 23, and each single every word is a token, right? So you have a token type and you have a token struct, and it has a type which is of token type and literal, which is the literal string itself. So then you define the types for everything. You define a constant called let, which is of token type, and you define ident, assign, and in, plus, asterisk, and semicolon. This is enough. These types are enough to tokenize this sentence. So this is how you are giving some sort of meaning to this string by defining everything in the string. Which means you can imagine like you have some. This is just a single line of code, but you take some other programming language, you write like 500 lines of code. There are so many things, like there are so many combinations of things. So everything will be. I will start with this kind of definition. They would have given some meaning to the numbers, the variables, and the keywords and identifiers. And after that, you define the Lexer. We define the Lexer struct, and how this Lexer operates is it takes in this whole string, and it will have index. It will have an index starting with L. This is the 0th index, and that will be stored in the position, and the read position is the next one to pick the next character, and character is the character itself. So, and we have this. Okay, yeah, that's not my system. How do I? Yeah. That's better. So we have so you define a method on the Lexer struct called next token, and it is a bunch of switch cases. So if you encounter equal to, you assign the new equal to token which you define here, right? So you have this token type assigned So you initialize a new token type. So if you come across plus, you initialize new plus token and so on. And if you come up, if it's not a part of these cases, then it means it's either a letter or a digit, and depending on that letter or digit, it will execute this part of the code. So this is not a working code; it's the pseudocode I wrote, and it follows Golang syntax and semantics. So what happens here is like so we have initialize the lexer for this line, and it starts with position will be 0 and the index will be L. So of course the character is ch is L is stored inside the ch, and then when this logic executes, it finds out it's not equal to, it's not plus or other operators. It goes into default and it just reads the identifier. Now it moves to the pointer moves to the next position. So what read identifier does is it's kind of hidden, but read identifier would have some logic inside that which will compare whether it's it should see whether it's left or something. If it starts with L, it should be left. So let me move this index to 3 positions, and then I'll read the identifier and it will store it, and then it comes back. And since the index is moved, now the index is at the white space, and if you call next token again on this vector, so it will there is a white space, so it will skip the white space, and then the index moves to the next character. It reads the keyword, and now it skips the white space, and it goes to equal to, and it gets a new equal to token. And it goes on and on like this. So depending on the case, depending on the character you encounter, you assign a new token to that, and finally you get this. So far, do you have any questions? So I have a lot of time, so it's kind of 30 minutes off, but I think let you ask questions and I can drag it to 45 minutes. So you get the point, right? So how you are passing a simple string and adding some meaning to that by using those types. And then, so once you have some sort of meaningful token, you need to pass them. So, parser takes the tokens from lexer, and it will just put it into a data structure for you. Okay, I should stop using the word just. It is not that simple. It puts the tokens into a data structure so that you can, navigate through the tokens and try to evaluate them. So I've heard of this a lot. ASP Python talk everywhere. People talk about ASP. What is ASP? Of course, I've written that. So we just abstract the syntax and store it in a data structure. That's all ASP is. It's nothing complicated. It's just a tree/graph structure where you can store the tokens. You can use any other data structure to store your tokens, but there is a reason why you need a tree structure, because if this is our expression, right? 5 plus 2 into 3, and you can't evaluate it. If you store it in a list, you can't evaluate it like this. 5 plus 2 into 3, it won't give you the correct result. So you need some sort of operator weightage and precedence. In order to do that, you need a data structure which where you can navigate based on the weightage. So you need to first navigate from 3 and 2 and find out that there is this operator, product operator. You need to evaluate that. So in order to, this is the only reason you use abstract syntax tree. And so we need to define our ASP. In order to define ASP, we need to know what is an expression and a statement. So expression is something I would have heard about this a lot, but I don't know. Even I didn't know this definition properly until I came across this. So expression is something which doesn't return anything. Return a value. Sorry, it returns a value. So expression returns a value. 5 plus 2 into 3 will return 11 to the left hand side. So statement is something which doesn't return a value. It states something. when you type this, a is equal to or something in when you assign a variable in your interpreter, in your Python interpreter, probably it won't return anything. Sometimes it will return. It depends on the language. In Go, it won't return anything. In Python and JavaScript, it will return none or something. So, this is the expression statement. So with this in mind, a bunch of expression statements. Of course, it is a program, and now we need to define the nodes for our AST. So we have a token. We need to store tokens in a data structure. So we'll have a interface called node, and it has two methods: token literal and string. And you don't care about the method. It's just to make other interface satisfy or other struct satisfy that interface. So probably I think the string will return when you do dot string. The string will return the string of the token. So we have the type expression. So again an interface, and it embeds nodes in itself, and it has a method called the expression node, and we have the statement interface and statement node method, and a program. So we can relate to this. You don't have to understand the protocol, but you can just relate to this visual and something scribbled over there. So we are defining the components of a single line of our code as our node, and now we need to define an identifier to store our variable or the value of the variable. So the identifier is a struct which has a token, which has a token and a value. Token will be the identifier token which we created initially, and the value will be the literal value of that, like double quote a string. And we also create something called let statement, and let statement is let statement has a token, a name, and the value as an expression. So this kind of holds the AST node, and this represents our let statement. So here we are going to see only this single line of code, but if there are like for loops, if there are like some other statements, switch cases, if you're writing all those, you'll be creating either a struct or a class depending on your base course programming language, and you'll be creating the AST nodes for each statement. So here comes the parsing. Now we have AST nodes defined. We know that we have a meaningful tokens, and we have AST nodes defined, and we need to parse the tokens and just fill in the AST. Okay, not just fill in the AST nodes. It's going to be difficult because it uses recursion. So there are two types of parsing. One is top-down and bottom-up. It's obvious. Top-down parses the AST nodes from top-down, root node to leaf node, and bottom-up will be filling up from the leaf node and finally finishes with the top most root node. So top-down, there is something called top-down precedence parser, which is built by Naren, and it's also called SAP parser. It's one of the easiest parsers and easiest parser comparatively, but it's not easy. Even I don't remember the exact logic. So okay, before that, just I didn't do everything. I mean, it's like I followed a book and I did everything. I didn't create programming language out of the blue. I'm not the language. I forgot to mention that. Of course, I'll be mentioning this later. But so that book had that parser, and I read the papers, and I tried to understand. 2 months back, I was like, I knew what was happening, and right now I'm like, okay, what's happening? So yeah, recursion is hard. So this parser, what parser does is it, as I said, you need to fill in you need a meaningful data structure with the weightage, right? That's what parser does. It parses your tokens and gives you AST. So there's going to be a lot of recursion from now on, just 2 recursions, but I think I'll try to explain And yeah, to understand recursion, you must understand recursion first. So let's try to understand recursion. Okay.
Yeah, slide is in recursion.
Recursion. Yeah. Oh, yeah. Okay. Yeah. This reminds us that you should have your base condition properly, or else you'll just get stuck into infinite recursion because loop. So this start parser, it has like it operates on three concepts. So whenever it encounters a token, it will classify it into two types. Or one is, it will see whether it's a prefix expression or an infix expression. So prefix expression is something which can operate without left context. So if you just do -5 into your into your interpreter, it doesn't need the context what's happening on the left side of the expression. So, but if you do 5 plus 3, it needs to have it needs to know what's on the left side. So it will store 5 first, and it will try to add plus 3 to that. So these are it operates on these two concepts, and it also has something called precedences. So we'll be assigning some sort of weightage to every operator. The good old what they call board mass, which you study. Yeah. So they never told you this, right? So yeah, and so we will define our prefix expression and infix expression. So we have a prefix expression struct. Am I audible at the back? Yeah. So you have it has a token, an operator, and right expression. So prefix, you don't need the left context. So you just have this you have this token, and imagine the -5 it has operator, and you'll be storing it inside the operator field, and we have the expression which is on the right. For infix expression, you need to know both left and the right context. So you have token, left operator, left expression, operator, and right expression. Then you will be defining two functions. One is prefix function and infix function. So based on the expression you encountered, you just you pass them into these functions. So we'll see the pseudocode of that too. Before that, you have a before that you have a let statement node. I think this is going to be the root node. So and it has the name a, and it has a value which we defined earlier. So now we are going to parse the value and going to build the tree, and that is going to be stored inside the let statement struct. Okay, now we have our there are like three functions. One is parse expression, where you'll be passing your expression, and it uses infix expression or prefix expression based on which kind of expression it encounters. So so what happens like when you pass this, you don't have to read the code, just follow the arrow mark, and you will get an idea of how the recursion happens. So when you pass this expression, just a second. Yeah. So when you pass this expression, the first token which is passed is like 5, and it is a prefix expression. 5 is a prefix expression, so it calls the prefix expression, and it will find that it is an integer, and it will just initialize the integer node. Then it comes to the parse expression, and it will see whether there is a semicolon, and it will also check for the precedence, and based on that it goes into the for loop, and now the next it will pass the infix expression. So the infix expression is the plus operator. So the left operator here, if you just follow the arrow marks, and if you see the left expression is 5, and the right expression operator is the current token, which is plus. and then you assign this as okay, this is confusing for me. Assign input expression dot right. Oh, okay.
We'll have to switch it anyways. I think we remove there. That's it.
Yeah.
Oh, shit. Okay. No, switch the laptop to that side.
Right. Okay. So once it passes the okay, let's go again. The question is hard. So what happens is like you're passing, you're giving 5 into this expression, and it passes, it identifies it as prefix expression, and then it goes into this method and finds out it's an integer literal, and then it comes back to that method, that function, and it's going to pass the infix expression. At that time, okay, the index changes to plus, and the left expression is 5, and the operator is plus. Okay, it's stored as left expression. Got it. And okay, right. So it is inside a recursion, and this, there is a the stack call which has pause. It has left expression as this these two nodes, and then now we're trying to pass the right expression, which is right of this index 2. So you're again calling the pass expression, and it's like one stack is paused, going the recursion to the same function again, and you're again doing a parse prefix expression. So what happens here is 2 is a prefix expression, so it again finds that it's an integer literal, and then it goes into this loop, and next one is a infix expression. So it goes and it gets to the initializes the infix expression struct with 2 as the left expression and operator as the current token. So this index moves along with when the recursion happens. Now the next expression is right. So now we have now the second call stack is paused, and you have these 2 nodes, and now we are going to call parse expression again. So this is like what do you call it? This is like we are interchanging, like it's like calling other methods recursively. It's not like recursing in one method. Like it's calling each other method. That's why it's confusing. So and again you're calling the parse expression 3rd time. So this time you have 3. It is of course a prefix expression, and it is an integer literal. So you create an integer AST or integer literal node, and then finally it doesn't go into this. So it is kind of a base condition, right? So it had its base condition, and now since it's encoding semicolon, it's not going to this, and it returns. So now the stack starts returning. So once it returns the h.n6 expression, and it will be stored inside where is the right expression? Okay, that's how it happens. All right, so maybe you should go and look into it. But you got the idea, right? So it happens recursively. So like the thing with recursion is even if you're writing the recursion logic, just make sure even touch the recursion logic, like you forget it. So, and now we just built the recursive. We just built the ASP tree recursively. Now we need to evaluate that. Right now we have we took out this meaningless string, and we tokenized it, and we assigned some sort of token, and then we put that into a data structure. Now we need to evaluate the data structure. Before that, let's see what usually evaluator does. So evaluator takes in the ASP tree, and it will give you the expected output, which is the 11 in our case. And sometimes before giving you the output, it will convert it into bytecode. And I think even Python interpreter does that. It converts into bytecode, and it runs over a VM. You have seen PYC files, like compiled files. So, and it runs on Python virtual machine. So you won't. So it looks like you say that Python is an interpreted language, but if you notice that it is compiling and using PYC file and then interpreting it line by line, because it makes it a bit more faster. And yeah, so JVM and YARP are the VMs which is used in Java, and as well as yeah, I think it's yet another Ruby VM. So these are the VMs used in Java and Ruby to run the interpreter, interpret the bytecode, compiled bytecode. There is to make it even faster, there are some languages which directly converts the bytecode into machine code. Of course, Go does that. So it's like you have when you use Go, you won't be having any kind of VMs. It'll be just building a binary for your server. This could be Ubuntu or macOS or whatever it is, and it'll be just running the binary right there. It will come as a single binary package. You don't need any sort of VM. Or if you take Java, you have to install JVM, or you need to do some sort of packaging to run it without any dependencies. Yeah, so that's called just-in-time compilation. So let's build an evaluator. We need to take in the ASP tree, and we need to get the expected output. So to build this evaluator system, we need an object system to keep track of the data. So you need so you need to store A, right? So next time if you're using this value again, you need to pull up this value from somewhere. You don't have to go to all this ASP to find out the value of A again. You need to kind of cache the value. So we define an object type. Object type is a string, and there is an object interface which has type and inspect. I think inspect is just return the string of the literal string of the object. And we have the integer object type, and we have the integer struct. So yeah, you have the integer object type, and you make it satisfy with object type interface by defining the methods type and inspect. And in order to store the environment, you'll be using the environment struct, which will have a map behind the code. So now we can imagine how your when you just reuse a variable, how it is stored. It's probably some kind of hash map or some kind of order of one call behind that. That's how it's written. So we have the let statement A, and we have the value of that, which is this whole ASC tree. We need to start evaluating it. So this is the pseudocode for eval. So based on each case, you'll be calling it recursively. Recursion again, I think it will be easier. So based on let statement, you'll be if it's let statement, you will eval the value and pass on the environment. If you notice that you'll be passing on environment everywhere, right? So because you need to keep track of the environment, you need to store this value of A inside the environment. And if it's identifier, this means okay. Let me just start this first. Initially, you pass in this root node, which is a let statement. So again, it's called eval recursively, passing in node dot value, and the node dot value is the whole ASP node. Once you pass in node dot value, it is going to evaluate left and right node. So you eval left node, and then left node, you again this recursion starts again. So it goes inside the eval again, and you find that it's an integer literal, and then you evaluate right node recursively. Then it finds, then it doesn't go into integer literal. The green is where the pointer is on, the stack trace is on. So it doesn't find, it finds that it is an in-six expression, the type is in-six expression. So it goes into this case, and again it starts calling left and right. Now we evaluate left by recursively calling the same method, same function, and we find out that integer 2, and we evaluate right, and we find out that integer 3. And then you have the left and right. Now, okay, before this, we find in the next eval call, we'll be finding out that it's an ASP operator is product. So now we calculate this, and we return the product. Similarly, in the next call, we'll be getting into this condition, which is the ASP operator is plus, and we will do 6 plus 5. So you get the object or the object is 11 now. You get the final result, but you can get the idea, right? How it is getting evaluated, and why ASP specifically. You are evaluating it by giving. If you use a list, you won't get this result, right? So you are evaluating it depending on the precedence and weightage. That's the reason why you use ASP, and if you use Python or if you go there like ASP libraries. So when you enter the when you type the code and when you try to call that library to give you the ASP behind the code. So next time when you type, just type a very simple expression and use that inbuilt standard library, and see you will be able to relate whatever you saw here. Now, that's all. Okay, so I'll show you the code. Is it visible? Is it? No?
I thought I was the one who was getting old now. I think everybody has the same problem.
Yeah. Now? Better? No. Can you switch off the first line?
Yes, I can.
Now? So, of course, the code is like some 5,000 lines, so I won't be able to show you all the code. So you can see these packages, right? Lexer, we have a Lexer, parser, evaluator, and object system, and of course a REPL. So let's start with the REPL, and here REPL is basically what the REPL you see in your Python Python interpreter, read, evaluate, print, loop. It's called REPL because it does that again and again inside an infinite for loop. You can see there. So I'll show you some important thing. You can see this line, right? If you remember, we created a Lexer struct, and that struct is getting initialized with a single line. So the line which we saw, let a5 equal to, let a equal to whatever, it is this string, and it is passed into this Lexer. And we call this parser dot parse program. Here's what all this if I click this p dot parse program. Here's what the recursion, the parsing starts, and the recursively parses. And there is the environment where we have defined a struct and environment struct, and we're going to store all the variables inside a hash map. So it has a bit more complex logic here because you need scoping. So you need outer environment and inner environment. If you add, you can just embed. You will be embedding the outer environment. So whenever you have another variable defined inside a block of code, you need to first check the current environment, and if it's not there, you need to go to the outer environment. So that's what happens here. And the Lexer which you saw here, the switch statements of Lexer. So the parser will be calling dot next token in order to get the each token. So this is the method that this is the real code of the pseudocode which you saw. And AST is, I think there isn't much logic in here. We'll be defining all the interfaces, and it will be, if you see, like for Boolean type, there is a struct defined, and for if expression, there's a struct defined, and it should satisfy this interface node interface so that we can make this store into the abstract syntax tree. So let's try to run this code. Of course, it will run. Oh, by the way, I named this pet programming language as Sushi because I like sushi. So you can see this single statement which you saw in this first slide, it goes through all this logic in order to get you this result. So yeah, your compiler goes through a lot. Don't write bad code. It's already going through a lot. So I think this is all the functions too. So, but let me get back to the slide and wrap up. Why create a programming language? There are so many programming languages out there already. Why create one? So if you learn more about computers, right? So if you don't know how compilers work, then you don't know how computers work. If you're not 100% sure whether you know how compilers work, then you don't know how they work. So it's not necessary, but if you know how compilers work, you'll be able to do micro level optimizations whenever you want to do. Uh, so these days we have like so many abstractions, and it becomes the compiler engineering. It became like meaningless for application developers. But if you explore compiler engineering, you see like everything is based out of a bunch of papers in 80s and 90s, and I was yeah, that's why like it was so interesting for me. So instead of just learning some high level new tech, why don't they just get back to the get back to where everything started, and just explore from there. And Lexus and parsers are not just used in compilers and interpreters; they are used everywhere. So if you're writing a DSL, for example, your SQL uses Lexus and parsers now to parse your SQL queries, and if you use a YAML, the YAML engine uses the Lexus and parser, and it's used in JSON. So there's serializer and deserializer, and also your search engine. So Elasticsearch tokenizes everything. It doesn't search just on a simple string. So Lexus and parsers are used everywhere, and you can see through the syntax. So next time when you just read a func foo equal to or func foo something, or if you read some sort of Python code, instead of just seeing the syntax, just like there will be things to it, that you know what's happening behind that, and you'll be able to decode things, debug things better because I experienced that, and most importantly, it is fun. So it's like creating your own programming language, right? It doesn't matter. It doesn't matter whether there are so many programming languages. It's like you have your own programming language. And but while creating this, I have been through like so many papers, and I went through all the recursion algorithms, things, but still, I did that, and you would feel that the woman touched it, not of me, whatever it is. So it's like really fun, and it will kind of like pave me a way to it's just kind of give this path for me to think about independent researching. So since I've been reading a lot of papers, and also I've been reading some sort of books which which was taken as semesters in MIT. So doing all this kind of things will just put you with more confidence to write better code. And one more thing is like you will learn more about the host language, right? So in Go, even though I've been using Go for like 3 years, I didn't use interface to much extent. So I stopped with stuff because I didn't find a way to use. I didn't find the need to use interface. But here, this is one of the projects where I really understood why interfaces are there in Go. So it makes you to learn more about your host language, either it's assembly or C or whatever you're writing with, you learn about that language too. Yeah, the credit. So everything I spoke here, maybe just give me like 2% credit for providing these guys. Remaining credit goes to this guy, Dawson Ball, and you can follow him on Twitter. And he wrote this book called Interpreter Book. It's a very short book on the Facebook, fully hands-on. You'll be able to create a programming language if you complete this book. But don't copy the code. Type everything. I took some 4 weeks to complete the book, and I typed like 5,000 lines of code and wrote. I wrote like many test cases, and then references. So after reading this book, I spoke with him, and I found out that he wrote this book because he went through structural and SACP book. So it's kind of the legacy book for designing interpreters and programming languages. They talk about list, talk about scheme with a variant of list, and there's this blog post which helped me to refresh this brush up fast passing. I should have seen that before coming to this talk. So I went out of that. And there's this paper, there's this remastered paper from Pratt, and it is in t.github.io. You can also find the original paper there. Thank you. Yeah, so yeah, I can clap. So if you have any questions, So like past 2 months I've been like pretty busy and going solo and getting onboarding projects, so I didn't work much on this. But of course, like first thing of starting a side project is you spend so much on it, and I think I already did the first step, and probably by next year either I'll be working on this. Probably by next year you'll be finding a good documentation on sushilang.org, or else the domain name will be available for sale. Anyway, let's see. So if you have any questions, you can visit me on Twitter, and if you want talk officially, you can just email me. Pick me up on this email address, Naren@government.io. And thanks for coming to my talk. Also putting up with your questions. Any questions? Don't ask about the questions. Any questions?
Are there any programming language compilers
This book I talked about, it uses it has a programming language for Monkey, and it's almost he uses that programming language to explain to run through the code on production language. Not really, because there are compilers written in Go.
There is this thing called VLAN. VLAN is written in Go.
Because Go is 10 years old, and there are like programming languages which are like 30 years old, 20 years old. So I think it's I'm not seeing any production languages in Go. But if it's there, it would be either like this, or it might be in some beta state. Any other questions? You can find the slides on my website. And if you want any other resources on building smart, this talk is just to spark the interest and to spread the knowledge of spread the knowledge, to let you know that computer engineering is interesting, and can go explore, and to give you some resources. So if you want to talk more about it, I'll be around here, and also keep me up on Twitter.
There is one question in the chat. So is it open source? Is the question, and can they contribute?
Yeah, it is open source, but there is okay.
It's in the chat. So yes, they are on the call. So.
Yeah, it is for us that it is open source. We can definitely contribute it, but as you saw, I forgot before to say about a month back, so I need to document it. So I need to document it. Probably if things goes well, I'll document it, and then you ping me somewhere, and I'll.
You said you were going to the compiler. Is there any GitHub repository, like an awesome paper?
Yeah, it should be there. I went to only specific. I didn't go to all the papers because whenever I found this new keyword, I was like, oh, what is it? It happened in 1970. I didn't know what it was found. So it's been like that. I didn't have any specific set of resources. As and when I encountered something, I just tried to peel away the abstraction and. But you can find I think you can find compiler specific papers in awesome papers. So there is a repository. I know about that. Yeah, so there are many other parsers too, but this fat parser is not something to use everywhere because it uses tree walking interpreter. So without changing, without converting everything into bytecode, it's just like you traverse the tree and just evaluate it. It is slower, but it will help you learn more about compiler. Any other question? Okay, then thank you. Thank you.
Naren, we have a small gift for you.
Food is also ready actually outside.
Okay, your pizzas are ready? Yeah. So we have a lot of people around to talk and share knowledge, so you can get ahead and do that. People who have joined online, thank you so much for joining, and we're gonna enjoy a lot of pizza. So next time, please drop in and enjoy the meetup. Yeah. Okay. There's a lot of stuff. Yeah, we have actually recorded the event, so you'll get that as a YouTube link soon in a couple of days. Thanks for joining.